you have access to a video that will be similar to if we had the slides. Let me pray for us. Father, thank you so much for this opportunity we have to meet and to just to learn more about these laws that govern your world. Father, I pray that you would help us to just to understand what's going on so that by that we might understand the Creator better. We ask these things in the name of Jesus. Amen. So this lesson 18, we're talking about magnetism. And I'm sure many of you have interacted with, I know you've interacted with magnets in some way, and you've probably interacted with magnets in a way in which you were doing so in a somewhat academic way, right? Trying to see what magnets are capable of doing. But I don't know how often you've asked yourself the question, what is a magnetic field? Right? So you have these magnets, and they cause certain changes and certain shifts and certain things to happen, and it's because of a magnetic field. And so the idea with a magnetic field is that basically you have something like this. Where you have your north pole of your magnet and your south pole of a magnet, and in between the two you have a magnetic field. And a magnetic field is any place in which a charged particle, like an electron, is forced to move in a circular way. It can't actually move through a magnetic field in a straight path. Okay? And so that it's kind of weird to define what a magnetic field is that way. But that's how we define a magnetic field. It's a space in which charged particles can't move in a straight line. Even if they're fired in there in a straight line, they will curve in response to that magnetic field. So another way to think about this is it's a space in which you have you're exerting influence over anything charged. And so the even setting up the magnetic field is accomplished by charge moving. That's how you generate an electric field, and so that's why charged particles behave a certain way inside of the field. And so there are two main ways in which you can set this up. The magnets we tend to create are those made by moving large amounts of electrons through a wire. So we have what are called electromagnets, and they're basically set up by they force an enormous amount of electrons to move, and as you do, you create two different charged terminals and generate this magnetic space, this magnetic field, where charged particles are going to move in particular ways. There are other ways to do it, and these are more natural, and this is where we make magnets out of magnetic material. So we just harvest magnetic material and build magnets out of them. We're not really generating the magnetism, we're just harnessing what's there. And these are made by small numbers of electrons, but moving among atomic nuclei. So where you'd have several different nuclei, and so these are all nuclei. And you have electrons that are moving back and forth. And so what we'll do is we'll just kind of draw a cumulative electron cloud. And so this cloud around these nuclei are illustrating places where electrons can be. And so you have basically this pool of electrons moving a great deal among these nuclei, and as a result generating this magnetic field. Does that make sense? Okay. And so the reason why, or here, let me ask you this. If you see this charged particle, this electron, being forced in a different direction as a result of this magnetic field, what's happening to that electron? What's forcing it to change its path? I'll give you a hint. I asked the question with a very key word inside of it. What's that? Force, right? There's some kind of a magnetic force that's forcing the electron to change its path. Because if the electron comes in a straight path, right, so the electron's coming in like this, and then all of a sudden it gets here and starts to change its path, okay, then there's some force acting on that electron. There's some force pushing it in this direction. Okay? And we call this the magnetic force. That's what F sub m is representing. It's a force like any other force, like a force of you pushing an object over, but it's a force due to the magnetic field. All right? But if something's going to change direction, there's acceleration. And if there's acceleration, there's some force acting on it, right? Because even an electron, as small as it is, still has mass. And if you've got an acceleration and you've got something with mass, you have force, because force equals mass times acceleration. Right? And so the question then becomes, all right, so we know there's a force here. We know that there's some force, magnetic force, that's, by the way, I drew this in a very strange way. I realized what I did, and here, I'll just erase it. Because if the electron's moving in that direction when it comes in from the south, it should also move in that direction when it comes in, from the north. And so the question that we have about this force is, how do we measure how strong this force is? How do we get an indication of the strength of this magnetic field, therefore the strength of the magnetic force? Have you all played with really powerful magnets? Any of you ever had some really powerful magnets and tried to separate them? I'll bring some of these to lab. We'll have some time during our last lab when we do some things with circuits. We'll play with magnets as well. But when you get some really powerful magnets, it's impressive, the strength of some of these magnetic forces. But we have a way in which we can measure the strength of the magnetic field. And so we do it first by recognizing that the magnetic field is going to influence an object in a particular way, and here's how we do this. All right, so we find the magnetic force. So F sub m is equal to this. Is equal to Q times V times B. Okay, that the magnetic force is equal to Q times V times B. Now we've seen Q before. What is it? We've seen it before as a capital Q, but in here it's still the same value. It's charge. So Q is charge. Let me go to our blue. So Q is charge. Actually, let's not go to the blue because that one's not good. So we'll go Q is charge. V, we've seen this before too. What is V?
Velocity.
Velocity. And what do you think B is? B is the strength of the magnetic field. The strength of the magnetic field. Now, B has a particular direction. There's a certain direction associated with the movement of charge creating that magnetic field. And so we can figure out the direction, the force, how that force is going to push, which direction the force is going to push on any particular object by the charge of that object, the velocity, which includes the direction that the object is coming from, and then the direction that the magnetic field is moving. Okay? So our magnetic force is equal to the product of charge, velocity. This is charge of the object. Charge of the object inside of the magnetic field, the velocity of the object inside the magnetic field, and then the strength of the magnetic field itself. So if you're looking at an electron, the charge on an individual electron is relatively small, right? It's like something times 10 to the minus 19 coulombs. Okay, a relatively small charge, a negative charge. Its velocity is incredibly high. Okay, not quite as far above zero as its charge is below zero. And then the magnetic field is going to do a lot towards shaping how much force you're going to exert on the object. But that makes sense, right? If you have a relatively weak magnetic field, you wouldn't expect to have a really strong force exerted on that object passing through it, right? Whereas if you have a really strong magnetic field, you'd expect a stronger force being exerted on the object. But the interesting thing is here is this magnetic, the force of the magnetic field, it's a little bit more complicated than just if we end up with a positive number, it's going to move to the right. And if we end up with a negative number, it's going to move to the left. Because when we're talking about magnetic fields, they occupy three-dimensional space, right? Which means that our force can operate in 3 dimensions. So if you think about a sphere, the force is going to be basically a straight line pointing at some point on that sphere. And we need to be able to figure out exactly where that force is pointing. So it's not quite as simple. It's like, oh, well, an electron is negative, so it's going to make this value negative, and we're going to point to the left. Okay? Because this is one of the few areas in like a high school physics class where you have to think in 3 dimensions. Most of the time we think in 2 dimensions. But for magnetism, we need to think in 3 dimensions, which is fun. It's fun. The way we figure out the direction of the force is using what's called the right-hand rule. So we use what's called the right-hand rule, and so we take our thumb and we point it in the direction of the velocity of the object. Okay? So you take your thumb on your right hand, it's called the right-hand rule, so you use your right hand, and you point your thumb in the direction of the velocity of the object. So in this case, we have our electron well, I'll use this one because this one is going to require me to put my thumb upside down. That's hard for me. So I'm going to use this one. And right now my thumb is up, right? That electron entered from the bottom moving straight up. You put your fingers in the direction of the magnetic field, which in this case I didn't indicate the magnetic field, but it's basically moving in this direction here. Okay, so we have our velocity here. We have our magnetic field is moving in that direction. And then your right hand is pointing in the direction of the magnetic force. So which means that the force exerted on this electron would actually push the electron out towards us, and not in the way that I drew it. I drew in 2 dimensions, I can't really draw in 3 dimensions, but in reality this electron would be coming out towards us, whether it entered from the bottom, or even if it entered from the top. Well, if it entered from the top, I guess that wasn't too hard to do the electron entering from the top. We have the velocity going straight down, the magnetic field is still pointed in that direction, and the force would be forcing the electron away from us. Alright? So we need to work some problems, and then maybe this, will start to come into play. Remember, thumb in the direction of the velocity of the object, fingers in the direction of the magnetic field, and then palm shows you which direction your force is going to push that object. Alright? So this is kind of cool, like if you were setting up a magnetic field, maybe we'll do this as well on our last lab, and we start shooting charged particles into it, you have an idea of which direction they're going to go. We'll see if we can make something like that work. That would be a lot of fun. All right. So this first question I want to deal with is, what is the strength of the magnetic force felt by an electron moving at the speed of light through a magnetic field of 5.00 Teslas? And the nice thing here is it just says, what is the strength of the magnetic force, which is just telling us what is the magnitude and not what is the overall force. Okay, so let's keep that in mind. All right, so what do we have, or what are we given? And this one I'll actually write out for you since you can't see this problem. What do we have? I almost combined have and given and wrote haven. So what do we have? We have that the strength of the magnetic field is equal to 5.00 Teslas. Oh, I didn't tell you that from the last slide. The units that we use to measure magnetic field are Teslas. Okay. So the strength of this is 5.00 Teslas. We also know the charge. The charge on an electron is, I think, negative 1.6 times 10 to the minus 19 coulombs. That 1.6 sounds like it's the right number. We've seen this number before, and I don't have it written down, but I'm pretty sure that's the charge on an electron. So we're also given that because it told us we had an electron. And then we have a tool. We have a tool that says that the force, the magnitude of the force, we're just doing magnitude right now. We don't need to know directions because luckily this problem asks us only for the strength of the force, just the magnitude. So force is equal to charge times velocity times the magnetic field. Oh, that's another thing it gave us. It's felt by an electron moving at the speed of light. I didn't write that one down, so we also know velocity. Velocity, we've seen this before, not in a while. The velocity of the speed of light is 3.0 times 10 to the 8th meters per second. All right. So we have our tool. Bless you. And the question, and then it's like, well, okay, well, what do we want? What is this problem asking us to determine? And it really just wants the magnitude of the force. It doesn't ask us which direction is that force going to act, just the magnitude. And now our tool is already set up to solve for that. So we have our force is equal to our charge, negative 1.6 times 10 to the minus 19 coulombs, times our velocity, which is 3.0, times 10 to the 8th meters per second, times the strength of the magnetic field, which is 5.00 Tesla. And these units, they get a little bit strange when we do this. Ultimately, we should be able to get our units down to newtons, right? Because that's what force is measured in. But it's a little bit complicated to demonstrate how that works. So right now, we'll just leave our units in coulombs, Tesla, meters per second. You okay with that? All right, so we've got 5.0 times 3.0 times negative 1.6 times 1.6 times 10 to the minus 19. And we get, this has two significant figures, this has two significant figures, this has three significant figures. But if you wanted to, we could assume that these are exact values. I wouldn't, just keep those as 2. And so we have negative 2.4 times 10 to the minus 18 coulombs Tesla meters per second as the strength of our magnetic force. It's the strength of our magnetic force. And again, you can go through and figure out how does that whittle down to newtons, which is what we measure force in, but it's a little bit more complex than what we need to do. Right? Now, what would you need to know in order to figure out the direction of the force? So we know the magnitude. What would you need to know in order to figure out the direction? You know it. We need to use right-hand rule, right? So in order to use right-hand rule, we got to put our thumb in the direction the electron's traveling. So we would need to know what direction is the electron traveling. And we put our fingers in the direction of the magnetic field, so we would know which direction is the magnetic field. Yeah. Moving in. All right? See if we can't set some of a problem up like that. Oh. We'll do actually one more problem without using right hand rule. Sorry, the way the slides are set up now, I don't see what's coming next, and so it's a little bit of a surprise to me. But that's fine. We'll leave our have, want, and tools up. All right. So I'm going to give you what this problem asks us. If the strength of the magnetic force, so we'll say F sub m is equal to 7.50 coulombs Tesla meters per second on a particle moving at exactly 5 times the speed of light. So our velocity is equal to not 3.0 times 10 to the 8th, exactly 5 times, so 15 times 10 to the 8 meters per second. Notice I left this in two significant figures, so we usually do it as 3.0 times 10 to the 8, and I did exactly 5, so I'm not going to limit it to one significant figure because it said exactly 5, but I will limit it to 2, the 3.0. So 15 times 10 to the 8th, and then assume the charge on the particle, so we know that the charge, which is Q, is equal to 5.55 times 10 to the 6th coulombs. All right. So tools, we still have the same tool that says magnetic force is equal to Q times V times the magnetic field. And then this problem wants to know what is the strength of the magnetic field. What is the strength of the magnetic field? All right, so this is one where the algebra is not super complicated to rearrange our tool. So we'll go ahead and do that, because this wants us to solve for B. Wants to know what is the strength of the magnetic field. Again, right here we're not dealing with direction, we're just dealing with magnitude. And so it's only part of the story, which is a little sad, but it is a good part of the story, dealing with magnitude. So if we wanted to solve this for B, what would we do? We divide both sides by Q times V. Right now Q and V are both being multiplied to B, and we'll divide this side by Q times V, so we end up with a tool that says B is equal to magnetic force divided by Q times V. Now, do we know all these values? Look back to what we have or what we're given. Are we given these three values? We sure are. So do we have everything we need to find the strength of the magnetic field? We sure do. Okay, so B is equal to our magnetic force, which is 7.5 coulombs, Tesla, meters per second, divided by our charge, which is 5.55 times 10 to the 6th coulombs. That's a particle carrying a lot of charge. Figure an electron has a charge of essentially 1 times 10 to the minus 19. It's 1.6, but it's, this is a huge charge. Times our velocity, which is 5 times the speed of light, which is 15 times 10 to the 8th meters per second. And yes, I know that this is not proper scientific notation to say 15 times 10 to the 8th, but I knew that eventually we'll be in a situation where we've got to rectify this, and so we'll deal with it then. Okay? So coulombs are going to cancel. Meters per second are going to cancel, and we'll be left with units that are Tesla. Is it set up correctly algebraically? It is, because we're ending up in the units that we want, right? We want to have Tesla because we're doing strength of the magnetic field. So we're going to do 7.5 divided by 5.55 times 10 to the 6th power divided by 15 times 10 to the 8th power. And we get, this is 3 significant figures, this is 3, but this is only 2. So we will present our number with 2 significant figures, and we get a number of 9.0 times 10 to the minus 16 Tesla. 9.0 times 10 to the minus 16 Tesla. This is a tiny magnetic force. Would you agree? Times 10 to the minus 16, that is a tiny magnetic field. Sorry, not magnetic force, magnetic field. So why is the force so strong then? It's a very weak magnetic field. So why is the force so strong? The particle has a huge charge, right? And the particle is moving extremely fast. So this gives you a good indication that it's not just, you don't just depend on the strength of the magnetic field to determine how strong that magnetic force is. You also depend on how fast and how much charge that particle's carrying. Okay. Which just creates some fun things you can do in the lab with magnets. There are multiple ways in which you can create an intense magnetic force. All right? Okay, let's do some problems using the right-hand rule. And then we'll talk a little bit more about just some structural issues. And then if you guys have any more questions about how to work some of these problems out, we can do that as well in preparation for your homework and your exam. So, yeah, for those of you that aren't in class right now, we don't have power, so nobody can see what's on the slides except for me. So it's just creating some interesting dynamics that I wasn't ready for when I prepped, but that's okay. So this problem says if an electron is moving east and the magnetic field points north, which direction is the magnetic force? Which direction is the magnetic force? All right? So if we want to orient ourselves to where, we kind of know what's going on, let's see, this way, basically almost perfectly this way would be north. This way would be east, south, and west. It's not quite that perfect north, it's actually I think a little bit that way, but we'll just say it's this way for simplicity's sake, okay? So, and it's almost perfectly this way. So if the electron is moving east, what do we point in that direction? We got to point our thumb in that direction, right? So we're going to point our thumb over to the east, which again, we're assuming north is exactly here. Again, it's more that way, but it's fine. So we're going to point our thumb to the east, and then in the magnetic field points north. What do we point north in? Our fingers. Okay, and so we put our thumb to the east, our fingers pointing directly to the north, and which is the direction of the magnetic force? Straight up. And see, again, it's different because for the first time we're operating in three-dimensional space. And so if you were to fire an electron, so you've got a magnetic field that's pointing directly north, and you were to fire an electron to the east, as soon as it got into this magnetic field, the force would start pushing it up. Now it's still going to keep going that direction because that's where its initial velocity is, right? And it's just going to curve up in this way. It should be kind of fun. Kind of fun to do. Again, we'll see if we can make some of this stuff work. All right. What is the direction of the magnetic force on a particle moving along the y-axis if the magnetic field is directed away from the observer? Okay. So what is the direction of the magnetic force of a particle moving along the y-axis? So let's erase this. Now we're not talking east-west. We're talking about x-y axis. So we're talking about how we normally represent two-dimensional space, and then we'll bring it into a three-dimensional space. All right. So we've got a mention of the y-axis. So what we'll do is just draw our coordinate plane. You've all done this before, right? Operated on the coordinate plane. So we've got our x-axis here. We have our y-axis here. Gosh, that looks like an x. Okay. We've got our x-axis there, we've got our y-axis there, and then it says, okay, what is the direction of the magnetic force on a particle moving along the y-axis? So where do we point our thumb? Our thumb is going to be the direction of the movement. Now notice this doesn't tell us if we're moving positively on the y-axis or if we're moving negatively, which means we're going to need to account for both. So we'll do our initial where our thumb is pointing up along the y-axis. Okay? And then the magnetic field is directed away from the observer. So if you are the observer, how do I direct my magnetic field away from you? Where do I point my fingers? Into the board. Okay? So our particle's moving up, our magnetic field is moving away from you. Where's the direction of the force? Yep, in the negative direction on the x-axis. Right? What about if we had the opposite, where the particle is actually moving in a negative direction on the y-axis? Our magnetic field is still operating away from the observer, and now which direction is the magnetic force pushing it in? In a positive direction on the x-axis. Okay? So notice it has a big bearing on what actually happens. So when I redrew my figure earlier, I did it correct the first time, incorrect the second time. Because the velocity changed direction, so the magnetic force should push in a different direction. So it was right the first time. I'm so sorry. I thought, gosh, I should have just left it. There's a whole thing of, like, you shouldn't go from your first answer, because your first answer was probably right. Or at least has a higher probability of being right than your second answer. All right? So the velocity, because velocity has direction, it has a huge impact on the direction of the magnetic field, or the magnetic force, not of the magnetic field, but the direction of the magnetic force. And it's because the velocity has direction, right? Velocity doesn't just have magnitude. Direction matters. Just like for our magnetic force, it's not just magnitude. The first two problems we did, we were just worried about magnitude, but direction is also important. So for those first two problems, we could go back and we could put in some directionality. Maybe that's what we'll do. Are there any questions right now? Y'all don't feel particularly handicapped for having not had access to the slides, so you can't see the question written up on the TV? It's kind of fun. We lost power in the middle of my last class. And so all the students were like, oh, cool, class is going to be over. And I was like, no, class is not over. And it's class bigger than this. There are about 30 people, and I taught the last half of the class in the dark. I just opened up some doors so we got some light in there, wrote big on the board. It was good. All right? So let's think about those first two problems, and to think about how starting to add direction would give us some clue as to which direction our magnetic force is going to act. We already know magnitude. In the second problem, it actually gave us the magnitude of the magnetic force and wanted us to figure out the magnitude of the magnetic field. But do you guys still have those problems written down? Okay, so go back and look at the first problem. First problem is, what is the strength of the magnetic force felt by an electron moving at the speed of light through a magnetic field of 5.00 Tesla? Now, what would we need to know in order to know the direction?
Which way it's
We need to know which way the electron is traveling, and what else? The direction of the magnetic field. So let's say for this one, and what was our answer for the magnitude of the magnetic force?
negative 2.4 times
Negative 2.4 times 10 to the minus 18. It's a pretty small force. Okay, but let's say our electron is moving along this line here. So the equation for this line is y equals x. Right? Okay, so let's say the electron is moving along the line y equals x. Okay? And let's say it's moving in a positive direction. So it's moving in a positive direction on the line y equals x. So where does our thumb go? Like this, right? The positive direction along the line y equals x. And then let's say the magnetic field is directed towards the observer. Okay? So now I need to move my body so I can accomplish this. Thumb in the direction of the electron travel. Fingers in the direction, towards the observer. I got carried away. So our electron is now moving positively on the line y equals x. Our magnetic field is oriented towards the observer. Where's the magnetic force directed? Downward. So it actually is in a negative direction on the line y equals negative x. Okay. That cool? It's not cool. Is that understandable? Okay, cool. That's cool. That it's understandable. All right, so the next one, the second problem we dealt with, we were given the strength of the magnetic force, which is a huge, oh my gosh, it was times 10 to the 23rd. Nobody even corrected me when I did that. Oh, that's because you didn't know. I wrote down what do we have, and you don't see the screen. Oh, gosh. I just expected you to correct me with something that you don't even have access to. Gosh, I need to learn how to operate without power more often. So the magnetic force was supposed to be 7.50 times 10 to the 23rd power. But anyways, so we had magnetic force was given to us. The velocity was given to us, and now we needed to find the magnitude of the magnetic field. And so now we have to do the right-hand rule in a bit of a different way. So let's assume that our particle moving at exactly 5 times the speed of light was moving in a positive direction on the y-axis. Okay? Positive direction on the y-axis. And let's assume that our magnetic force was actually oriented away from the observer. Okay? So our particle is moving in a positive direction on the y-axis. The magnetic force is oriented away from the observer, so my palm needs to face the board now. And then it's like, okay, well, which direction is the magnetic field? The only way to accomplish this is if the magnetic field is moving positive on the x-axis. Okay? So you can use the right-hand rule even given some other features. Well, let's assume we had a problem that said something like this. That said, you have a magnetic field that is moving towards the observer. Okay, so we still have our xy coordinate plane, and we have a magnetic field that is moving towards the observer. So we don't know what to do with our thumb or the palm of our hand, but we know that our fingers need to be oriented towards the observer. Okay, fingers are oriented towards the observer, and then it says the magnetic force is oriented directly positive on the x-axis. Okay, so right now my hand is in the correct placement, right? And then said, okay, what direction is the velocity of the object? How would you describe the direction of the velocity of the object? Yeah. Now notice it'd be positive on the y-axis. Okay, right? Positive along the y-axis. Notice if we keep the direction of the magnetic force the same, the palm still facing in the positive direction on the x-axis, but we change the direction of the magnetic field, what happens to the velocity of our object? Or better yet, let's ask it this way. If we keep the magnetic force is oriented in the same direction, but we change the velocity of the object, what has to happen to the direction of our magnetic field? It's got to change in order to accomplish the same magnetic force moving in the same direction. And so since we're operating in 3 dimensions, if we change any of those 3 dimensions, and you want to keep one of them the same, the other has to change as well. Okay? Two have to change if one is going to remain the same. But one can remain the same all the time. So there are the reason why I tell you that is there are a number of ways in which you can generate the same magnetic force. In our physics class here on campus, it's a general physics class. They're covering magnetism right now. And our professor had a whole handful of magnets. I should have brought some for our class. But I think he's hoping probably that the lights will come back on in time for him to have his class. But we've now had the lights off for about an hour and a half, and they haven't come back on yet. So, any questions about magnetism? It's a little weird operating in 3 dimensions, but it's manageable, especially with this whole right-hand rule. It's a very quick and easy way to visualize what you're doing, because we're used to operating in 2 dimensions. So it's nice to have a means by which we can interact with the 3rd dimension. And I mean, we do this all the time in our normal life. We don't do it very often in our physics. Okay? And so the important thing for determining the direction of our magnetic force is the direction of our velocity and the direction of our magnetic field. Noticing we don't care all that much about the charge. Okay? We don't care all that much about the charge because our right-hand rule just tells us velocity and the direction of the magnetic field. Okay? All right, but what do we care about when we're trying to determine the magnitude of the magnetic force? We care about charge, we care about the magnitude of the velocity, and we care about the magnitude of the magnetic field. Right? So we have 3 things really influencing the magnitude of the force, and really 2 main things influencing the direction of the magnetic force. All right? Any thoughts, concerns, things you want to share? Knowing that Malachi and Isaiah can hear you, anything that you want to share with them? All right. Sorry, Malachi and Isaiah, for things being a little bit different, but we don't have power. Sorry, everybody else, for things being a little bit different, but we don't have power. So it's the joy of living in Southern California, right? Actually, really, you have power issues regardless of where you live. Ours aren't due to weather. Ours are due to usage. So when you get a usage spike, sometimes you get a blackout or a brownout. Yeah.
Why is it out right now?
I have no idea. Yeah, I have no idea. I haven't been free from class long enough to figure out if we even know. Most often